I will. Okay. Hi. So this is a review of where we are. GMW and YAO, two-party MPC, Boolean circuits, both honest but curious behavior. So far, and both of them can be extended to n party, and with full threshold of malicious of so if n party are participating, you maintain the secrecy property of MPC, even if n-1 players are. So HBC stands for passive attacker, right? So following the protocol. Okay. For GMW, this extension is okay. So that actually would be another exercise. Okay. Even if you fail to do this extension fully, it's a good thing to try to do. For YAO, so both extend to n party, but YAO is harder to see, I think, and the n party protocol is already part of the GMW paper. Here, the extension was subsequent work. Okay, so we'll the other branch, coming up is the Bgw, Benor, Goldwasser, Wittgerson. It's there, so I think 88 or 89. Okay, I forgot. Protocol, which is natively T of n threshold MPC for T smaller than n². Okay. So this one is built on Shamir secret sharing. And maybe we should recall also here that both of these are well, to or extendable to the full n party with full set of faults. Okay, and what sharing do they use? Okay, so GMW uses, they basically they use XOR sharing. So this is what the GMW uses explicitly, right? Like every value on the Boolean circuit is XOR shared between the two players. For YAO, this is not visible in the two-party sharing. It's a different form of sharing, but once you extend it to n party, this will be happening there as well. Okay, the Bgw protocol, which is built on Shamir secret sharing, it's an arithmetic circuit in a field. So the domain of secret sharing is natively, it's you embed all your inputs into a field. And in a field, you can add and multiply. And the gates of the circuit that you're computing are multi and add gates. And for certain fields, it is possible to put in all Boolean computation embed into arithmetic circuits. It's not a particularly efficient embedding, but it's feasible, and therefore these results also imply general secure computation of, in particular, you can, if your computation is described as a Boolean circuit, you can map it into this. But also some computation is natively arithmetic, and therefore these computation would is better suited for this. And okay, so we will do that next. But first, today I want to focus on this part. Okay, so how to upgrade to fully malicious participants. Okay, so okay. Just one more word. In both of these, the essential tool that allowed this was OT, oblivious transfer, in both of these protocols. For GMW, OT is the tool. Like, there is really nothing else happening. It's a black box. Once you get an OT, you get secure computation. You don't need anything else. For YAO, it's on OT plus the circuit garbling, right? So for YAO, there is one more thing adds to it, the circuit garbling. Okay, and we will revisit this because OT is the bottleneck for these protocols, and efficiency-wise, I mean, okay, it's one of the bottlenecks, so it is the main one here because that's the only tool here used, and it is, and for many computations, this would be a bottleneck for YAO. So we'll revisit the OT extension protocols that make this more efficient. In fact, each of these is a topic of active research, and there is surprising results for, you can, another sort of set of what was believed to be hard to bridge efficiency bottlenecks are surpassed with the ongoing research. So, well, okay, we'll at least, show some flavor of this, hopefully with OT extensions. Many things here are quite surprising, and we haven't seen the last of it. Okay, but let's do this one today first. So okay. So topic of the class, right? What did we get so far? We have zero knowledge proofs for all NP, and we have HPC secure computation. So HPC secure computation means that there is a protocol that, okay, let's think of two parties. And that's indeed what we have really shown so far. Two parties engage. There is a protocol such that if the counterparty follows the protocol, then I will have no qualms to engage in a secure computation of a function I know. Okay, if I think that, okay, evaluating this function on my database, say a health database of a hospital, with my counterparty, who is another hospital, if I think that I put my database, and whatever this guy puts, okay, this is me, and this is my counterparty, possibly. I don't fully trust them, because if I did, why don't I just give them the whole database and they give me their database, and we can very efficiently locally compute whatever it is that we want to compute. So the secure computation is this magic black box, right? So MPC for F, that at the end is just going to give us F of X Y prime, and what it will give to this guy is also F of X and Y prime. Now, based on, I know what F is, and I know that my counterparty's freedom is to pick any Y prime. Okay, perhaps they doctored their database so that to extract most information about my database, right, from the resulting evaluation of F. But if that's what I'm afraid of, whether I can just put in some conditions inside of F that would test that the inputs are viable, okay? Whatever it is that I think is like a doctored database, why don't I just add to the circuitry of F the verification that it's plausible, right? This is, okay, the full understanding of what, if people wanted to do this in practice, like, how would you put, right, these kind of checks? Well, these are application specific, okay? So, but this is something that I'm willing to engage with, right? HPC secure computation allows me to do so, right? Because whatever I do in the protocol, what the view of the MPC protocol that P2 has on his input Y prime is simulatable, is indistinguishable from a view that a simulator produces who has his input and the Z, okay? So the Z, which is equal to F of X, Y prime, okay? So the simulator can produce this view. And therefore, whatever it is that I'm revealing about X in the computation is indistinguishable for what can be learned just from adversaries' inputs and adversaries' outputs. Okay. But the guarantees of the two protocols that we have seen so far were for only passive faults. In other words, the view of the protocol is indistinguishable from a simulation only if the P2 star is P2. Okay, so this is a party who follows the prescribed protocol on the inputs. Okay, so in the case of GMW, it's a party that shares these things correctly, performs all the OTs correctly, and then reconstructs the outputs based on the right, that correctly reconstructs the final shares. In the case of Yao, if P2 is the circuit garbler, right, then okay, he created all this garbled circuit correctly, right? Okay, the exact ways in which you can embed faults into these protocols there are many, and And I think that they are a good exercise to do. But just this one of the something that happens to all of them is that well, they have always some form of sharing of the inputs. Even in Yao's garbled circuit, this sharing is the OT phase, which basically P2, the garbler, he knows the randomness used in the garbling, and P1 has all the garbled wire keys corresponding to all the inputs. That is a form of secret sharing, right? Because this guy creates all the garbled keys, which is for every input wire of the circuit of F. There's two keys, right? The 0-bit key and the 1-bit key. So P2 has a table of which key corresponds to which bit. P1, in order to start evaluation of the garbled circuit, has from that table, he has exactly one key for every input wire. He has either the 0-bit key or the 1-bit key. For his inputs, he knows, because he knows his inputs, right? So he knows that, okay, this is for sure the 0-bit key because my input there was a 0. But for the other guys, he doesn't know. He has some key, but he doesn't know, is it a 0-bit or a 1-bit key? But the two tables, the table that P1 holds of all the actual keys on the wires and the lookup table that the P2 has that contains both, right? They form a secret sharing of the input. Okay, then there is a computation, and then the final phase, reconstruction of the output. What was it in GMW? In GMW, there was an invariant that the sharing is just an XOR sharing of every wire. So at the end, they have an XOR sharing of every wire. What do? They broadcast the shares to one another, right? They exchange the shares. What was it in Yao? This guy ends up with the evaluation of all the output wire keys. And then with the lookup table, he can compute the output and then send it to P2. Okay, so the opportunity for P1 to cheat P2 are obvious at that step, right? Like he just sent him a wrong output. Okay, in a GMW, the same, right? Like P1 can get the share for P2, reconstruct the output locally, and then take his shares, and he already knows what P2's shares are, and so he can custom make his shares so that to convince P2 that the output is an arbitrary string of P1's choice, right? Okay, so, and that doesn't end faults that are possible, that just sort of the obvious ones at the end. They can basically cheat one another about what the output was. Okay. So, but we have this beautiful tool, right, of being able to prove that whatever you do is correct. So here is the immediate apparent compiler from honest but curious. So can we take an honest but curious MPC and zero knowledge proofs and give MPC for malicious attackers, for malicious attackers, right? How would this compiler work? So, okay, let's do two-party. So let HBC MPC be a protocol for party 1 and a protocol for party 2, okay, where the P1 is really a protocol for what the party should do in the first round, what this party should do in the second round, and what this party should do in a final round. So let's say there is k rounds in the protocol, number of protocol rounds. Okay, and likewise P2 is specifies what P2 should all do in all these rounds. Okay, and so the syntax would be that P1 on his input X and randomness R, where R is chosen from some randomness. Let's say the protocol is asymmetric, like Yao's garbled circuit protocol is. So they use different randomness, right? So what is P1's randomness in Yao is the randomness used in OT. That's really the only thing P1 does in that protocol, right? Right, and afterwards it's deterministic. He just evaluates the garbled circuit. And P1 outputs two things. Okay. So this is the randomness of P1 for whole protocol, right? It's not just randomness he needs in the first round, it's the total randomness he needs in the whole protocol. So this outputs the message 1 of the first player, so message of the first player in the first round. And let's say that P1 is the player that goes first, okay? It's up to renaming, right? So P2's first round protocol takes input Y and message that he got from P1, and the randomness which P2 takes from a different space. So this is randomness of P2 throughout the protocol. Okay. In the case of Yao, what is this? Well, what does Yao do? First, P2 garbles the circuit, right? So he needs what is garbling, okay, in the basic Yao's construction of garbling, picking random keys, two random keys per every wire in the Boolean circuit. That's the randomness, right? After you pick 2 random keys for every wire, the garbling is deterministic, assuming that the encryption used for, in the garbled tables for every gate is deterministic, but okay, it usually is. Symmetric key encryption. Well, okay, actually, no, it usually isn't, right? So there is also, if you have a wire, okay, that enters many gates, same wire is an input to many gates, G1, G2, G3, G4. Then this gate will contain ciphertext which look like encryption under, so let's call this wire W. KW0, okay, under this key of, well, of course, the gates are Boolean gates, so they have some other wire here, but we ignore this one for now. And under this key, you have to encrypt the key corresponding to these are output wires. The key corresponding to the output wire of this gate, and which one? Well, the G1 on 0 and whatever here. Okay, and here, so you have a bunch of these encryptions. I mean, actually two for the two possible keys, right? And the two possible values of Z1 on G1 on 0, this will be 0 and this will be 1. Yes, for two output values here, there is this key KW0 is acting on two ciphertexts. And so it will be here too, right? You will be encrypting some outputs of Z2 and what, so the keys corresponding to the Z2 wire on this bit and this bit, right? So here I use this key with a 0 bit, and here I use this with the 1 bit key for this wire, etc. Right? Because I need to do this now also for this and also for that. So how many encryptions I have under this key? Many, right? So two ciphertexts per gate, which uses wire W as input, will use KW0 as a key. Now, what do we know from basic symmetric crypto? If you want to reuse the key to encrypt many different things, you better use randomized encryption. Okay, now there is a way to avoid that because each of these wires have certain placement in the circuitry. You can use the index of this gate as a counter so enc needs randomness. Instead, use gate and wire indices as in CTR mode. Right. So instead of randomness, basically, I have unique indices of these objects. So I can use an index of this gate and a wire to basically derive a counter which is unique, and therefore I will avoid randomness, right? Okay, so sorry, maybe that was too big of a detour, but okay, anyway, so perhaps this randomness is just the keys, and the rest is deterministic, but there is also randomness in OT, right? This, by the way, is also like a good question. You can see, okay, can you do OT? Can you do commitment without with one party deterministic? And the answer is no. Okay, we're back to recording. Sorry about that. So, okay. So P2, given this message, will create, will output a message, the first message of the second party, and P1, the second round algorithm, will use these inputs and the message that he received, and the randomness, which was supposed to be picked just once, right? So this is not the most natural way to go, right? Like you don't this party basically, but you see, he might not use all the randomness here to create this, right? He used some. The second round algorithm will use the next batch of randomness, whatever it needs, right? These are fixed algorithms, so they know how much of randomness was used by this one and which bits here I should look if I need randomness as well. Why don't we need MSG, this message as input here? Because it's deterministic output of this, and we already have both X and R1, right? So this thing creates the message of the first player in round 2. P22 uses the messages it has received so far and the randomness, right, to create a message, second message of this player, etc. Okay, and without loss of generality, basically the case round looks like this. I have an input, all the messages that I have received from the counterparty for I 1 to well, looks like K for P1, and the randomness. And I'm outputting what I'm outputting message, my own message in the kth round, except so okay, okay, except so okay, sorry. So maybe this should be R in the round index. Okay, no, except that it was used for randomness. Okay, let's make it N, total number of rounds. Okay, and let's keep this being K, except if K is the final round at where output of P1 K is the final output of P1, right? So rather than this being a message that you send to the counterparty, this is actually your local output. Okay, and the same for the other party, right? So P2 in round K on input Y, and the messages it has received so far, which I guess goes from 1 to K minus 1 for P2, and his randomness, what he generates is the no. No, it's
the opposite.
This thing, yeah. 1 to K minus 1, right? So P1 actually in round 2 he only had messages from the previous round, while this guy will have messages all the way to his right, and okay, and he generates this. Okay, so how about we upgrade it to the malicious to security against malicious participants. By attach to message that you use in round K, zero knowledge proof that that there exists randomness input X and R such that the message at K is an output of the algorithm P at round K on inputs X. The basically, let's call it transcript, the stuff, and R. Okay, where the transcript goes, stands for messages from counterparty. And I'm not differentiating between what P1 and P2 does. You see that it's symmetric, right? So it's just some party, and he's following the protocol is known, right? So everybody knows what is the protocol that a party is supposed to follow in GMW. What is the protocol that the party is supposed to follow in YAO? Okay, what does it mean exactly? Attach a zero knowledge proof. Okay, well, we have seen in zero knowledge that well, we have seen two things. First was that you can have zero knowledge proof, but they are interactive. And you can have non-interactive zero knowledge. The only one we have seen really was the one based on random oracle. And it wasn't for all NP, it was for languages of pre-images of homomorphic one-way group homomorphisms. So the statements were a bunch of group elements, and the witness was the pre-image in an exponentiation, for example. Okay. Well, you can have non-interactive zero knowledge for all NP. Okay, so because of these are feasibility results, so it's like sort of whether you have random oracles or not random oracles, it doesn't matter that greatly, I think. I mean, okay, it's just that even with random oracles, it's not particularly efficient. But well, and that's another very active topic. Is if the product, okay, if what this party does can be described as a succinct circuit, Boolean circuit, can you have a proof of zero knowledge that the succinct, that the circuit, Boolean circuit, is followed on some values, that whose efficiency is related to the circuit description. So for succinct circuits, you can have efficient zero knowledge proofs for that. What are these circuits in our case? Well, they aren't particularly succinct, right? Think of what this guy does in, either GMW or YAO. So first of all, I mean, okay, so in both of them, he's an OT sender. What kind of OTs we have seen, right? Like so far, we have seen them from GDH, right? So these are basically variants of El-Gamal encryption modified in a special way, so that to implement OT rather than standard encryption. So the protocol that P2 follows is this is an El-Gamal ciphertext or Pedersen commitment, And what he does with these inputs is that he uses them to encrypt. So follows exponentiation in a group procedure, right, to create this message. That's the circuitry that you have here. Okay, so you would have to render the exponentiation in a group as a Boolean circuit, and then use this generic result. So perhaps these are not very, directly relevant to making GMW and YAO proofs for GMW and YAO efficient. But actually, these OTs are examples of group homomorphisms, right? Because if the OT based on DDH, well, it's all based on exponentiation as a group homomorphism. Perhaps the efficient stuff that we have seen, the efficient zero-knowledge proofs for group homomorphism pre-images, could be modified to hit what the prover has to prove on to follow the OT. Okay, and that is indeed the case. So OT proofs of correct following of OT, in fact, will be implied by these efficient zero-knowledge proofs for group homomorphisms, one-way group homomorphisms. Okay, so but okay, so that was a little detour. So if this is a what is attached ZKP mean? If ZKP is non-interactive zero knowledge, then well, attach the NIZK to the message. Okay, but in interactive case, well, just run the ZKP in between each protocol round. Okay, so this guy sends his message, and then they follow the 3-round, 4-round, 5-round zero knowledge proof. Once they're done and P2 accepts, then P2 will send his message and follow the however many rounds zero knowledge proof. Some of the zero knowledge proofs, even if they don't use random or so they're not NIZKs, they don't create this expansion in rounds. So the Goldreich-Kahan generic zero knowledge for NP was 5 rounds. So this would mean that if you start with a n round protocol, you end up with a 5n result. Some of them though can be piggybacked. So the protocol, the zero knowledge protocol could these parties know this code, right? Everybody knows what these procedures are. Perhaps they can start the proof system before seeing this input, right? So when this guy is proving, he needs to know what his input was, right? And what his output is, right? So that in order to prove that he followed correctly, he created this message, based on the transcript, we include this. But a lot of the zero knowledge, perhaps they can pre-compute stuff. So if you look at the recall the basic intuition for many of the zero knowledge proofs. You sent a commitment, which was what? Which was a random instance of the proof of what you're proving, but on a random point that is in fact unrelated to the point on which you're proving. So this would be the let's say that everything here is like a group homomorphism. Okay, so this is the pre-image and this is the image. You can start proving without knowing your witness, because the proof system in fact asks you to pick a random point and compute this group homomorphism on it. And when do you need your witness? Actually in the final move of the proof, when you take the combine the one-time point and your witness in a linear relation. So these proofs can be piggybacked, and there is a lot of technicalities to make sure that it's secure, but they don't have to have this factor of increasing round complexity. Okay. So let's say, but for simplicity, let's say there are NISCs, right? So in other words, the protocol would look like this. P1 has XR, and what he sends here is the message, his first message, plus a NISC that there exists XR such that message 1 is an output of, you know what, let's drop the index of which player is talking, because it's going to be the same problem for either of them, that it is an output of P1 on XR in the first message. Then whatever the response is, the next round says, okay, I'm adding a NISC that there exists an XR such that message 2 is P2 on XR and the transcript. Okay, and I do this in each round. I'm sending the message plus a NISC that there exists XR such that message K is PK of XR and transcript so far. Okay. Do you think that that means, is it true that if P1, P2, sorry, if basically P1, P2, PK is HBC secure, then the above protocol is secure against malicious P party?
Couldn't there be a problem with the fact that the R's are not the same?
Okay, I guess maybe I need to put these indexes here.
Professor?
I'm talking about the first party, although it is symmetric. So the issue for the second party will be the same. this might look funny to you. Why am I saying that MPC secure is a protocol and I'm only specifying what P1 does? Okay, because as far as so there is some honest protocol P2, right? And I can still say okay, whatever P. Okay, so this statement is also given P2, right? So we know what P2 does. We're asking, okay, we already know that if this pair is known to be HPC secure, meaning whatever P2 does, these transcripts that are produced, right? There is a simulator that shows these transcripts can be all produced from just X and the final output of the computation. And now I want to argue that this attaching these NISX would imply that I can simulate even if P1 diverges from the protocol. But you know, rather than think about a proof methodology of simulation, just think whether attaching these NISX really stop all ways of cheating. So what is being proven in all these NISX? That there exist some inputs which make this true. Okay, so let me. Okay, do you see? Does any of you see a way to cheat for P1?
Couldn't we change the R's?
He passes his NISX. The NISX are fine. Okay, and so therefore the statements have to be true. Okay, it has to be true that MSG1 is an output of P1 on XR claimed here, and that this is also true on XR, on some XR, right, and so forth. So each of these statements are true because NISX are sound. Okay. Okay. So what? How do you see? Oh, sorry. I didn't. I had a. Sorry about that. I had a mic off. I mean, I couldn't hear you. Now I can.
Okay, so I guess maybe TRs are changing because each time we get a different XR, right?
Exactly. So there is nothing stopping P1 from basically having some witness here, called it X1 R1, and having a different witness here, X2 R2, and XK RK. Right? So yes, he's proving that he followed the protocol, but on inputs that kept changing, and the randomness that kept changing. Right? So no, because XRs in each NISC could differ. Okay, so what can we do to fix this? How can we make sure that the XRs do not differ in each round?
Commitments, maybe?
Exactly. So of course, commitment. Okay, so idea 2, add start by publishing the commitment to XR and extend NISC, all the NISCs to statement that call this commitment C, that XR that XR are committed in C, right? So so such a message. So we send now this commitment, and we say and such a message and XR in C. Okay. What does it mean, XR in C? That means there is a decommitment. So so there exists a decommitment D such that open of the commitment C using the decommitment D and XR says yes, right? So that's what you are extending this with one more witness, and based on binding property of the commitment. Well, think of this commitment as perfectly binding. Okay, so there exists only one opening. Okay, so if this opening exists, there is no other. Okay, so that's a simplest case. So now there is a more subtle thing. Okay, so now this switching the XRs between the protocol round is no longer possible. If the commitment is even computationally binding, hiding, right, as perfectly binding commitment must be, at best, well, by computational hiding, you haven't revealed what X and R are. So the fact of this commitment should not stop. Right now, you have to have a simulation from the other side, which has to show this commitment. But what it would do, it would commit to random messages and then simulate zero knowledge proofs, in which case, right, the simulation goes through whether or not the statement was true or not, and it will compile correctly. There is still a bug though, but that one is harder to see. Let me maybe, okay, if you see it, chime in. So, but okay, here maybe is the way to guide you to it. So you're proving that you followed the protocol for some input and some randomness. And once you fixed this input to the input and the randomness, there is no further way to cheat. You have to follow the intended protocol on the committed input and randomness, because otherwise, by the soundness of this NIZK, you cannot pass this. And it holds for every round. So once you commit it, you're stuck. And it doesn't seem like you can diverge from protocol 1 on X and R. Now, X, in the model, you were free to choose X. The input are up to each party, right? So whoever agreed to compute function f with you should have been aware of that freedom that you have, which is to choose your X in an arbitrary way. What about R though? An honest protocol is trusted to fix, so the HBC person, attacker, right, is trusted to follow the protocol. What does it mean? First of all, he does, or she, picks the randomness from the intended space and samples it truly at random, and only then runs the protocol on it. So that's the final thing. What this compiler still doesn't do is to force the malicious participant to choose the randomness R correctly. It is so everything that you have seen about usage of randomness in cryptography should basically be like, wait, so what's the point of using running on bad randomness? Like, for example, if I want to encrypt, but I use bad randomness, I'm just shooting myself in the foot. If I use bad randomness when I choose keys, I'm just shooting myself in the foot. So it is natural to overlook this. How can a party help itself and cheat the counterparty? By just manipulating its own randomness in these protocols. But let's see. In fact, in GMW, how do you use randomness? These are random shares. Okay, so well, if I choose my shares that I give to the other party in some, deterministic or some other way than sampling them at random, the only thing I do is I give out information about my values, right? Because this is just a one-time pad. The shares that I give to the other guy are one-time pads. If I choose these one-time pads in a different way than uniformly sampling them, I'm only giving out information about my shares. Okay, but then there's one more thing that you do. Participate in OTs. Can you cheat in OT? How could you cheat in OT? Well, we don't know because we assume OT is HBC secure, and perhaps there is ways of cheating. If you look at these GDH-based OTs, well, in prime order groups, like, so if you implement them using RSA or some other, then there is all sorts of issues. You can choose elements that are not members of the subgroup that is intended, but some other one, and you have all forms of cheating. In prime groups, it's not so obvious, and in fact, you can show that these the basic OT that I showed you is secure against malicious participants. And it's so even if they choose randomness badly. Okay, so how do these players basically use randomness? These are randomness in El-Gamal encryption. Using bad randomness in this encryption and re-encryption can only well, it makes no difference to the counterparty. Okay, but here is one that it clearly makes a difference. Okay, and it's in Yao's garbling. Let me bring back a correct piece of paper with Yao's garbling procedure. Sorry, where's my Yao? Okay. Okay, it is. Okay, so you have to sort of see the whole construction to examine how can you basically mess up your counterparty by manipulating the randomness. In Yao, it is in the garbled wire, in the garbled gates. So the garbled gates for Yao are these encryption tables. What if what we needed for these encryption tables was that the property that the evaluator will have one key for KL and one key for KR. He will either have KL0 or he will have KL1. Likewise, he will have either KR0 or KR1. Let's say that he doesn't know which one is the case. Let's say that he holds KL1 and KR1. So he tries to decrypt this, it fails. He tries to decrypt each of these three. The only ciphertext which he should be decrypting is this one. What if the garbler picks the wire keys so that KL0 is actually equal to KL1? And for the good measure, KR0 is also equal to KR1. Well, in this way, clearly each of these four ciphertexts will decrypt correctly just by design. And he will get, let's say that on the output wire, he didn't cheat, so there were different values for the bit corresponding to 0 here. Let's say that the gate was XOR. So this was K out 0, this was K out 1, this one K out 1, this one was K out 0. So the poor evaluator gets this correctly formed garbled gate on correct set of wire keys, right? And it doesn't help that the garbler commits what is the randomness in Yao, all the randomness used in the garbling, first of all, and then also the randomness used in OTs. But first of all, randomness in the garbling. So this is this whole set of K10, K11, K20, K21, right? For all wires, 2 keys per wire. So he commits to all this stuff and then proves in zero knowledge that what the message is the garbled circuit, which is a collection of these garbled gates, that each of them is created correctly on all these committed in here keys, right? So all the wires are labeled. Let's say the first gate input is first wire, input is left to right, output is second wire, and the output is the third wire. These keys are committed in the known places in this string of commitment. So you can prove that you are encrypting, the correct wire key committed under these committed input wires, and you can do that for every gate. And so what? Who prevented you from forming the keys incorrectly, so that to lead the decryptor to this bad fault? And you can say, well, if you do that, aren't you just preventing the P2 from computation? Because he can simply say, well, if I get to the state where P2, so let's amend the protocol by saying that if ever P2 encounters a garbled gate which attempts at decryption actually return 2 or more valid ciphertext, then he aborts. Unfortunately, that doesn't work, because the fact that in a circuitry, P2 gets to some gate with wire. So now the P1 should get more sophisticated and actually embed this fault only if the key here is a 0. Then if KR is a 0, then there's 2 gates that decrypt correctly. Two ciphertexts. Sorry, 2 ciphertexts in this in the garbled version of G6, which will decrypt correctly. If his key here was KR1, then there would be no ambiguous decryption. The garbler only created this fault if the key is KR0. So that reveals, right? Because this guy is gonna encounter this fault even only if the bit on that wire is 0. So P1 uses this fault as a backdoor to learn a bit somewhere in the circuitry. Now you can say, okay, it's just 1 bit. Well, so there is of course, okay, is that the only way to cheat? And one question, and another is, hey, a bit is sometimes a lot. Like, think of this as a password check. If I learn a bit about your password every time you try to authenticate to me, that right, then after 20 times I would get 20 bits, and that perhaps is more than enough to reconstruct your password. Okay, so yeah. Now, of course, for this particular construction, we can do some adjustments so that to make sure that that this compiler actually is secure. Okay. In other words, what we need is, okay, and I know this. So this is the last thing. So idea 3, strengthen the HBC protocol so that security goes for players that follow protocol but can set their randomness arbitrarily. Okay. In other words, all the randomness that they use, like for example, in a so actually we have seen really 2 examples, right? In garbling and in OTs, and in secret shares for GMW, but that one was rather immediate. And you can, right? So in a YAO, what would you do? You would basically you would extend the zero knowledge proofs to make sure to prove that the committed keys are not equal for any wire. And then you would use a special purpose encryption that has this key committing property. So there is no way to cheat for arbitrary keys, not for random ones, but for arbitrarily chosen ones. Okay, that is not so obvious how to do in asymmetric encryption, but you can do it. So you can handle it on the level of the symmetric encryption building blocks. Okay. And also, if you can do it on the level of OT, and I was vaguely, sketchily arguing that you can for the OTs that we have seen based on prime order groups and GDH, you basically you are done at this point if you strengthen the HPC protocol, the underlying HPC protocols to handle this setting. And if you can't, if that's hard, okay, then prepend the protocol above by secure coin toss. Okay, what is the idea of secure coin toss? The idea of secure coin toss is, can these people follow some protocol so that at the end they have this guy has a randomness and this guy has let's say a commitment to this randomness, and R is sufficiently random. Why do I say this? So perfect randomness is impossible for fixed round coin toss protocols. With abort. Okay, so here is the thing. P1 could, let's say that there is a protocol where P1 cannot control really the randomness that it came out, and neither can P2. So P2 does not learn what this is, and P1 cannot truly control it. But what P1 can do always is, if he's unhappy with it, he aborts. And that is something that, like, you cannot really do much, right? If he's unhappy, he aborts. So that fact already skews the randomness. But there is a way to characterize this. Basically, it's a random process that the only thing that you can do is to abort. If it's a random sample, you can either take it or reject it. And that doesn't sway, so it suffices that the HPC protocol is correct on just in case they follow on random, because that way of, yes, they can reject, but that means that it's still random every time. Okay, so basically, assuming that the protocol is correct, is secure on true random samples, suffices to argue security, even under, if you can sample and abort, and then say, okay, you know what, I had a network fault, can we P2 restart? And P2 says, okay, fine, I will restart. So P1 has the ability to cheat, which is basically like this: get a few of these samples and decide on which to run. However, they're all random, so they cannot be used to attack if the underlying protocol, is the basic one. So it's not the stronger. Okay, it just gives you security guarantees for true randomness. And maybe how do you do this coin toss? Commit to pick R1 at random from the same space, pick R2 at random, and send a commitment. And now this guy open. Right. If you want randomness only for one party, that's I guess you have to stop here. Yes. So only this guy will get what the final randomness is, and the randomness is an XOR, let's say. Okay. this is why is this a random sampler? Because at this point, the P2 have seen a commitment to R1, but by hiding of commitment that told him nothing about the real R1, and he had to commit to R2. So once it was open, the R1 was open, he cannot change this. So basically, C2 works as commitment to R with public shift R1. Yes, so the value that is committed in here is whatever is committed here XOR the public shift, right? Made public by this decommitment. It's clear that this guy learns nothing about the R, right? Because the only thing he learns about R is what's in commitment to R2, but if it's hiding, okay? So that's the coin toss, but it doesn't, escape from this basic thing that this guy at the end can abort if he doesn't like the resulting value. Okay, sorry to go over time again. And next time, I want to show basically more efficient ways for making sure that for malicious security for YAO, the so-called cut and choose protocols. So this is a generic toolkit. It works for every protocol. Okay, I mean so far in a two-party setting, but it can be extended to two more parties. But when you want to instantiate it, there is other tools you can use, and that are for now more efficient for some protocols, including YAO, first of all, but also applicable in other contexts. So we will look at them next. Any questions? Okay. All right. So I already went over time. So I'll see you next time.